Welcome to another lecture on CS575. So this time we will see the implementation of the model, basically the building strategy. So the box Jenkins approach uses an iterative model building strategy that consists of 3 steps. So we have already seen, but we again see here in more details. So first step is selecting an initial model. So you select an initial model. Now, if I say with respect to ARIMA, then you can have an AR model only, a MA model only, right? You can have a ARMA model. You can have the complete ARIMA model with differencing also. Second is estimating the model coefficients. So what happens here is, for example, you might check for multiple models, right? So given a data set, depending on the features it has, whether it is seasonal, non-seasonal, trend, no trend, you can set multiple models and have multiple parameters. So for example, in ARIMA, right? So ARIMA basically consists of P, which is the partial autocorrelation, how many lags it is significant, D is differencing, and then Q. So let's say it is possible that for a given time series, you feel that there are more than one model which seems apt for applying on the data set. So let's say you have a PDQ, let's say 210. This is a particular ARIMA, and the next we want to test is, let's say, 110. Right. So among these two models, which model basically gives you a better fit? Right. So we will see those, how to estimate the model coefficient. Of course, the ones we usually do in ML on other practices is we compute the MSE, right, mean squared error, or we can compute RMSE or Nash Scutleft. Those are the methods, but we will also see how to analyze the model complexity using AIC, Akaike information criteria, and BIC. The last one is analyzing the residuals. Now, what are residuals, as we have already seen? So for example, let's say this is our original time series, and okay, we can take like this. Let's say the blue one is our original time series and the red one is the predicted one. So residual is basically the difference between the original time series and the time series that we have obtained. Right. So basically the difference between this point and this point, right? So this should have been the actual point. I am denoting it by A, and this red one is the predicted point. So the difference of these 2 point values basically gives me one residual. So let's say you have a time series predicting 100 points. So you have a data set of 100 points and then you do a prediction. So you will have 100 predicted points and 100 actual points. You take the difference of these two, that remains the difference. Basically, you will get 100 points, and those are nothing but the residuals. So we also analyze the residuals, right? So initially we will look at the model selection, then estimation, and finally after you fix a model, we see the residuals. We analyze the residuals. So if necessary, the initial model is modified and the process is repeated. So for example, you select a particular model, let's say ARIMA 210 and this model, then you check for this particular thing, you identify that this model is a better fit, and then you analyze the residual. So there is a property that we also calculate the ACF and PCF of residuals, and it should basically correspond to a white noise under ideal condition if the forecasting is done good, right? If that is not the case, we restart this process iteratively, right? So this is an iterative process and it is repeated until the residue indicate no further modification is necessary. That means, so the when you plot the ACF and PCF of the the residues, you will have all the residues within this 95% of the interval, right? So I hope these 3 steps are clear. Now let us see model identification. So in this approach, we select an appropriate model among the large variety of ARIMA models possible. Why it's saying large variety? Because we have possible values of P, D, and Q, right? So ARIMA basically works on these 3 values. So we can have as many, a large number of models. Even though in the theory we say that the values of 0, 1, 2 for each of P, D, and Q suffices, right? So even if these 3 values are there, we get 27 possible ARIMA combinations, right? So first thing is what we do, we plot the data. That's it. That is simple. Not even ACF and PCF, we just plot the data. So we first identify any unusual observation. Unusual means it may possible that the data may have a trend, may have a seasonality, right? The trend can be an upward trend, a downward trend, or the data may actually be a stationary data, or it may be a non-stationary data, right? So if necessary, transform the data to stabilize the variance. So stabilize the variance is nothing but a constant variance. A stationary data has a constant mean and a constant variance. So if your data is not stationary, you cannot apply ARIMA and all AR and MA models. So you first make it stationary. After that, check the time series plot ACF and PCF for stationarity. So if the time series plot shows that the data is scattered horizontally around constant mean, right? This is the mean. If it is scattered horizontally around the mean, and ACF and PCF 2 are near zero quickly, right? So if you have a mega line and then some small lines, basically exponential line, then we can say that the data is stationary, right? If not, then we try to convert to stationarity. How do we convert? We use the differencing operator. So for non-seasonal data, right, in which there is no season like quarter one, quarter two, or yearly sales, we take the first differences. And for seasonal data, we take seasonal differences. So for example, if you have quarterly data, Q1, Q2, Q3, and Q4, right? And similarly for the next year, then what we do, we subtract the quarterly data of this year with the quarterly data of the next year. So this is seasonal differences. As we have seen that we may require that even after seasonal differences, if it is not getting stationary, we need to do a normal difference, right? Check the plots again, right? So it says that only a single differencing may not suffice. Check the plots again. If they appear non-stationary, take the differences of the differenced data. So this is second difference. So when the stationarity has been achieved, check the ACF and PCF for any pattern remaining. So this is how you do the model identification. Now there are three possibilities. The model may be only a AR model or only a MA model. So how do you check for AR and MA? So for example, there is no significant ACF. Now you remember, if you have ACF, you basically indicate towards a MA model. If you have a PCF, you indicate towards the AR model. Remember the ARIMA parameter P is for the AR. So PACF and the parameter P. You can remember like this, right? PACF and the parameter P. So P basically indicates for the AR thing. So if you have no significant ACF after lag Q, it indicates a MAQ may be appropriate, right? So we usually have this confidence interval, and let's say we have lag 1 which are above this 95, and we have other lags which are like this. So this means this can be taken as a MA2. Mind you that this is a ACF graph, right? For MA model, we only look at the ACF graph. If we have a PCF graph, then if after time lag P, it indicates, for example, after time lag P, if this spikes reduced, then we say an ARP model may be adequate. In the next class, we also see the examples associated with it. So seasonality is present if ACF and PCF at seasonal lags are large and significant. This will be clear when we see a particular example. So usually what happens, let's say this is your axis and this is your 95%. So a seasonal data, let's say this is 6 month, right? So a seasonal data may show a occasional peak like this, right? So this may be the zero, the first month, then the first month of the next year, then the first month of the next to next year. So this is this is observed for seasonal data, right? So you can see all other peaks are below statistical significance, but there are few peaks which are basically above the line of significance, and they are appearing after every year or quarter depending on the seasonality. If no clear MA or AR model is suggested, a mixture model may be appropriate. So in mixture model, what do? You try for AR and MA. You see if differencing is applied, you try for ARIMA with parameters P, D, Q. So these were the very basics of model identification. So you plot the data, check if it is stationary. If it is not stationary, try to make it stationary. Right after that, check for ACF and PACF. We will see examples in the next class. So that's it for this lecture class. Goodbye.